Welcome to the Honeywell RDR-4000 IntuVue weather radar pilot training for Airbus aircraft, including the new Hazard version 2.0 display features. The A380 is covered in a separate training video. This presentation was created by the Honeywell Flight Technical Services Group. This presentation is Honeywell proprietary information and is subject to export restrictions. This is revision 1, dated March 2018. This training is broken into modules. These modules will build upon each other, providing a basis for understanding and using the RDR-4000 system. The modules should be viewed in order. They will compare the RDR-4000 to conventional radar, look at the heart of the system, the 3D volumetric buffer, and the operational modes it provides. Towards the end, we'll pull it all together by showing some operational examples, explain how to deal with Stratis weather, and some in-service experience. The final module is for operators that have the Hazard version 2.0 display features installed. So let's begin. The RDR-4000 is much easier to use, but it's different. It automates many of the tasks required by conventional radar, but does them in a different way. So a good starting point would be a quick review of conventional tilt-based radar operation, and then we'll see how the RDR-4000 makes life easier. With the conventional tilt-based radar, the system sweeps an area ahead of the aircraft based on the selected tilt angle. There is a one-to-one correspondence between the antenna sweep and what is shown on the display. It provides reflectivity information in 2 dimensions, azimuth and range. For detection, most crews use a technique called the cruise ground park technique, or it could be referred to as establishing a protection zone. Whatever it's called, the technique is the same, lowering the beam until ground returns appear at the outer edge of the display. This technique has 2 main benefits. First, storm cells are easily identified because they walk out of the ground returns. And secondly, if there isn't a radar shadow behind the cell, then we know the radar signal hasn't been attenuated. This technique detects all cells, but analysis is still required in order to make a deviation decision. For analysis, we manipulate the tilt control and build a mental picture of the weather ahead. The vertical extent of the cell can be determined using the 1 in 60 rule. You remember the 1 in 60 rule from your early pilot training. If you are 60 nautical miles from a VOR station and 1 degree off track, you are 1 nautical mile off track. For radar, there is an easier form of the rule. Just take the range, add 2 zeros, and that will tell you how many feet 1 degree is at any range. For example, at 60 nautical miles, add 2 zeros, and 1 degree at 60 nautical miles is 6,000 feet, which is very close to 1 nautical mile. At 40 nautical miles, 1 degree is 4,000 feet. An air transport antenna has a 3-degree beam width, so at 40 nautical miles it is 3 times that, or 12,000 feet tall and wide. This simple rule can be used in several ways. First, the beam is extremely large at long ranges. At 320 nautical miles, it's over 96,000 feet tall and wide in this example. Second, close to the aircraft, the beam is very narrow and at high cruise altitudes is entirely in less reflective frozen ice crystals. This also explains why a cell detected at longer ranges requires continuous down tilt to track the cell as it gets closer to the aircraft. If not, it will disappear under the narrowing beam. And last, it can be used to measure the height of a cell. To explain, here is a quick example with our aircraft in cruise flight at 38,000 feet and a cell detected 40 nautical miles directly ahead. The analysis will be done relative to the aircraft altitude of 38,000 feet. Start by raising the tilt 1/2 of the antenna's beam width, or 1.5 degrees, for the 3-degree air transport antenna used in this example. That puts the bottom of the beam parallel to the flight path. Now raise the beam until the returns begin to disappear. Keep in mind the aircraft is at 38,000 feet, so tilting up will cause the radar to look mainly at less reflective frozen ice crystals. The gain can be increased to maximum, allowing us to better see the frozen particles and get a better measurement of the height of the cell. Now, increasing the tilt may be continued until the top of the cell disappears. The cell completely disappears at plus 3.5 degrees up tilt. The exercise started at plus 1.5 degrees, so the beam was raised a total of 2 degrees. At 40 nautical miles, 1 degree is 4,000 feet, so the beam was raised a total of 8,000 feet. The aircraft is at 38,000 feet, so the wet top of this cell is approximately 46,000 feet. The course of action in this case is obvious. The cell directly ahead should definitely be avoided since the wet top exceeds the aircraft altitude. There is always a trade-off when making a deviation decision. Analysis should be completed, allowing enough time to negotiate a deviation with ATC, but close enough to the weather to provide adequate resolution for effective analysis. At 40 nautical miles, 1 degree is 4,000 feet. At 80 nautical miles, it's 8,000 feet. And at 100 nautical miles, it's 10,000 feet. For cases where the cell is much higher or lower than the aircraft, that isn't an issue. The in-between cases are much more difficult to evaluate. Before moving on to the RDR-4000, a discussion about reflectivity, which is what a radar measures, is in order. Radar does not directly measure rainfall rate. It measures how much of the transmitted energy is reflected back to the radar. The amount of reflected energy is proportional to the rainfall rate and is represented by the different colors on the display. The colors give us some indication of the probability of turbulence and hail size. In the chart on the left, at the beginning of red, 40 dBz, it indicates a 40% chance of moderate turbulence and a 5% chance of severe turbulence. The same with hail size probability. This isn't the probability that there will be hail, but rather if there is hail, what size it is likely to be. Well, there is a 100% guarantee that a flight through this cell would encounter turbulence. And at the bottom of the previous slide, there was a note stating that the chart was for convective weather. So there is a need to first determine the weather in question is convective and not stratiform for the chart to even apply. And so the radar should be used as a tool to detect convective activity, not just rainfall. Convective activity is detected by looking at the vertical development or extent of cells and how much moisture is carried aloft. So altitude is the important third dimension. Conventional radars only provide range and azimuth information. The RDR-4000 captures altitude information and uses it in the automatic detection and manual analysis modes to provide additional information to assist in making deviation decisions. The RDR-4000 is subject to the same physical limitations as a conventional radar, but it provides modes to help reduce workload. As the description of the RDR-4000 progresses, note how altitude information is incorporated to help the pilot make informed decisions. In the first module, we will examine the heart of the RDR-4000 system, the 3D volumetric buffer. One of the first things you will notice about the RDR-4000 system is there is no tilt control. The system automatically and continuously scans and collects weather and ground returns from the nose of the aircraft out to 320 nautical miles and from the ground to 60,000 feet. For scans above the freezing level, the system automatically increases the gain to make less reflective frozen storm tops more visible. The scanned information is stored in a 3D volumetric buffer, or memory, and is continuously updated and compensated for aircraft movement. The data is also corrected for the Earth's curvature, so the altitudes displayed by the system are true MSL altitudes. If left uncorrected, the effect of the Earth curvature can be quite significant. In the picture shown, the aircraft is at flight level 250. However, because of the Earth's curvature, the center of the beam is above 27,000 feet at 60 nautical miles, almost 37,000 feet at 120 nautical miles, and 44,000 feet at 150 nautical miles. The automatic scanning stores all of the weather and ground return information in the 3D buffer memory. The system also contains an internal worldwide terrain database that is a version of our EGPWS database, but without airports, runways, and obstacles. Because the RDR-4000 uses only the terrain information, regularly scheduled updates are not required. The terrain database allows the radar to distinguish between weather and ground returns. We can then display just weather information in the weather modes and only ground returns in the ground map mode. In the ground map mode, the ground returns are provided by the radar returns and not the internal terrain database. This allows for an independent verification of position. Other information put into the 3D buffer includes enhanced turbulence data. Turbulence detection is automatic and is provided out to 40 nautical miles for any range selection if enabled, 60 nautical miles if you have the hazard display features. The RDR-4000 is the first system certified to the FAA's new Enhanced Turbulence Minimum Operational Performance Standard, or MOPS. It provides more sensitive and accurate turbulence information with fewer false alerts and improved correlation to predicted aircraft G-forces. It is also up to 12 times more sensitive than current systems. Think of the 3D volumetric buffer as a giant Rubik's Cube that goes from the nose of the aircraft out to 320 nautical miles and from the ground to 60,000 feet. Each square is at a certain position in range, azimuth, latitude, longitude, and altitude. In each of these squares, information is stored about reflectivity, turbulence, and if the return is from weather or ground. Since there is no tilt control, the pilot is not using the control panel to control the radar, but rather using it to request information from the 3D buffer. This is what allows our system to provide pilots with independent selections of ranges, modes, and altitude slices. This information can be presented in many ways, including comparing the buffer data to the aircraft's flight path and displaying the weather on the flight path in solid colors as shown here, and weather outside of the flight path displayed in a hashed pattern as shown here. This display is from the A380, which includes a vertical display of weather, shown here as an example to illustrate how weather on and off of the flight path is shown on the nav display. The pilot can also extract Earth curvature corrected altitude slices out of the buffer and display them on the ND. Here we have the same storm cell with slices extracted at 12,000 feet and 22,000 feet. This analysis mode provides a simple means for making deviation decisions. The next module will describe the operational modes provided by the 3D buffer. In the final module of this video, we will describe the optional hazard display features and associated control panel. There are several minor changes which we will point out here and then cover in more detail in that module. There was a change in the naming of the auto modes on the new control panel, but they all work the same. All mode on the new control panel is called All WEX mode, and On Path mode on the new control panel is called Path WEX mode. As we go through these modules, All and All WEX can be used interchangeably, as can On Path and Path WEX. Collectively, these are the auto or automatic detection modes of the radar, and when we don't need to differentiate the modes, we will just use the term auto mode. One other change has to do with turbulence detection. With the standard control panel, turbulence is displayed in all and on-path modes out to 40 nautical miles. With the new control panel and hazard display features, turbulence can be displayed in all WEX, path WEX, and elevation modes out to 60 nautical miles, which is an additional 20 nautical miles. Turbulence can also be selected on or off with any of these modes. Now that you understand the naming, we can discuss the operational modes, and the auto modes will be discussed first. The auto modes are the automatic detection modes of the radar. These are the modes that you will be in most of the time. They provide strategic weather detection, and in most cases you can also use the auto mode for avoidance. Later we'll talk about the unique analysis mode the RDR-4000 provides to help you with more difficult situations. Airbus aircraft have two forms of auto mode called All and On Path, or as just described, All WEX and Path WEX on the newer panel compatible with the hazard display features. In All or All WEX mode, the system analyzes the data in the 3D volumetric buffer and compares it to the aircraft's vertical flight path. It then shows weather in the flight path in a solid pattern and weather away from the flight path in a hashed pattern. Here are some examples. In the first one, the aircraft is straight and level below 25,000 feet. Both storm cells are a threat based on the flight path, and the display would look like a normal radar display with both cells displayed in solid colors. The normal envelope around the flight path is plus and minus 4,000 feet for weather. Turbulence information is displayed plus and minus 5,000 feet around the aircraft's altitude with the standard control panel. Now the aircraft begins a climb to cruise altitude. The cell closer to the aircraft is in the flight path envelope and is still shown in solid colors, but the second cell is now way below the flight path and will be shown in a hashed pattern indicating it is outside the flight path. Flight path is determined by using vertical rate and ground speed and is extrapolated out to 60 nautical miles because we don't assume the aircraft will climb or descend forever. At 60 nautical miles, that altitude is used as the flight path beyond 60 nautical miles. In this example, the aircraft is at cruise altitude, but beginning a descent. Based on the new flight path, the second cell will change from the hash pattern to the solid pattern, indicating that it is now in the aircraft's flight path. The normal envelope around the aircraft is plus or minus 4,000 feet. However, when the aircraft passes through 25,000 feet, the bottom of the envelope becomes fixed at 25,000 feet and goes to 4,000 feet above the aircraft altitude. Most inadvertent turbulence encounters, especially at night, are due to less reflective frozen storm tops. The RDR-4000 system does several things to make these cells more visible. First, in the collection process, the gain is increased when scanning at higher altitudes. Second, the floor of the flight path envelope never goes above 25,000 feet. And third, what is displayed is the maximum reflectivity at any point from 25,000 feet to 4,000 feet above the aircraft altitude. With the Hazard display version 2.0, there are some modifications to the fixed lower boundary of 25,000 feet, which will be covered in the Hazard display section. The 3D scanning, increased gain, and 25,000-foot floor provide a unique combination to protect crews from overflying hazardous cells. What the crew will see is live storm data, not predictions. This robust method has proven to be the best method of handling varying geographic weather conditions. This concept just described is very similar to the National Weather Service images. They provide two types of reflectivity data called base and composite reflectivity. The image shown is a base image. Think of this image as showing rainfall at the surface. On a base scan, the system uses a single tilt angle and shows the base reflectivity data. What is shown here is a single base scan on a column of weather, outlined in blue, that would result in green being displayed. A composite image is collected over many sweeps. In the next scan, the reflectivity is increased and would be yellow. In the next scan, the reflectivity is increased further and is red. In a composite image, the maximum reflectivity in the entire column is used. So in the left column, the maximum reflectivity is yellow. In the center, it is red, and on the right, green. Think of a composite image as a worst-case image. It is showing the worst possible weather, or maximum reflectivity, in a given volume. This is the result of a composite image for the same area. Looking at the two images side by side, the composite image shows more returns as expected. Base reflectivity is useful for showing where it is raining on the ground, but since airplanes don't fly at ground level, it is more useful to see what is happening at the higher altitudes. And this is what the 3D volumetric buffer essentially shows, composite reflectivity, but some enhancements have been added to aid pilots since airplanes fly at a wide range of altitudes. To better explain this concept, here is an example of a typical storm cell. The solid lines in the cross-section represent isoecho contours, or lines of constant reflectivity. At the top of the cell, the reflectivity is only 20 dBz, and would normally be shown as light green on the display. Notice the arrows in the picture. They represent the wind speed and direction within the cell. At the bottom, there is inflow into the cell, but look at the top. The arrows near the top of the cell are the longest, indicating they have the strongest updraft velocities, but would only appear as light green on the display based on the 20 dBz contour line. This is what it would look like on a legacy radar system. Close to the cell, the beam is very narrow and intersects the cell at high altitudes where the frozen particles are less reflective. Even though this cell had enough energy to lift moisture over 37,000 feet into the atmosphere, it would only show up as light green on the display. At cruise altitudes, for any given point on the display, the RDR-4000 looks into the buffer from 25,000 feet to 4,000 feet above the aircraft altitude and extracts the maximum reflectivity for each point on the display. So in this case of this cell, instead of just showing light green on the display, the RDR-4000 would show green, yellow, and red, alerting the pilot of the hazardous condition. The area above 25,000 feet is shown in solid colors as flight path weather, and the same thing happens for the secondary weather. The maximum reflectivity of the secondary weather is shown, but in a hashed pattern. Flight path weather always has priority over and covers secondary weather. So if there's hash red below and solid green above, the red will be covered by the solid green. Because the pilot will see more weather presented in a composite image compared to conventional radar, there may be times when it appears the system is oversensitive. It's not, but it's one of the differences you need to understand. The key is to always think about altitude first and then color. What the system is telling the pilot is this cell had enough energy to push moisture over 25,000 feet into the atmosphere. The solid flight path color doesn't necessarily mean that you will need to avoid this weather. It means the weather has penetrated your protection zone, should be monitored, and may require analysis. And for the same reason, it might appear at times that the system isn't sensitive enough. In this case, the height of the cell has been decreased, so the pilot only sees green above 25,000 feet. But remember, the flight path weather always has priority over and covers the secondary weather. So the flight path weather, which is green, covers the yellow and red at the lower altitude. But again, use the key. Think about altitude first, then color. The system is telling the pilot this cell has moisture above 25,000 feet, has entered your protection zone, and should be monitored. So how do you make a deviation decision? In a moment, we'll discuss elevation mode, and later on, show you some practical examples of how it can be used in conjunction with the auto modes to make effective deviation decisions. This is a more graphical representation of the auto mode. The translucent wedge indicates the plus or minus 4,000 foot envelope around the aircraft. Here, the aircraft is flying straight and level, and where the wedge intersects the cell in front of the aircraft, it is shown in a solid pattern. The low-lying weather off to the left is still shown, but in a crosshatched pattern. This table is in the pilot's guide, and while it looks somewhat daunting, it is really fairly simple. The normal flight path envelope is plus or minus 4,000 feet around the aircraft's flight path. As described, the bottom of the envelope never goes above 25,000 feet so that frozen storm tops are more visible. When the aircraft reaches 29,000 feet, which is 25,000 plus 4,000, the bottom of the envelope stops at 25,000 feet. Likewise, on takeoff, approach, and landing, the top of the buffer never goes below 10,000 feet, which is 6,000 plus 4,000. This allows about 10 minutes look ahead along the flight path. All or all-wex mode just described shows all the weather, both flight path and secondary. In on-path or path-wex mode, only the weather in the flight path is shown. This mode declutters the display by removing weather outside of the flight path. It is extremely useful for dealing with stratus layers, and we'll talk about this more in the module on dealing with stratus weather. Now let's look at the analysis mode. It is called elevation mode on the Airbus aircraft. This mode allows selection of Earth curvature corrected horizontal slices from the buffer, so they are true MSL altitudes. The captain and first officer can have different altitude slices selected. The initial slice will be at the current aircraft altitude and then can be dialed up or down from 0 to 60,000 feet in 1,000 foot increments. The selected altitude is maintained regardless of whether the aircraft is climbing or descending. For altitudes below ground level, nothing is shown on the display. In these pictures, the same area of weather is displayed with different altitude slices selected. On the left, a slice is taken at 12,000 feet, and on the right, a slice is taken at 22,000 feet. This mode allows the pilot to easily measure the tops of the cells to find a deviation path while never having to manipulate a tilt control or perform mental math. With the new control panel and hazard display features, you can also enable or disable the display of turbulence information while assessing a deviation path. With a conventional pencil beam antenna, the radar would display just a narrow swath of ground returns. The RDR-4000 pieces all of these narrow swaths together in the buffer to give you an extended ground map. Ground map is optimized for longer ranges, and weather returns are suppressed. However, over areas with very low reflectivity like water, some weather returns may appear. Map mode is useful for identifying prominent features like coastlines and lakes. The ground returns are actual radar reflectivity and not from the internal terrain database. This provides an independent verification of position. Ground map mode can also be used to identify areas of attenuation if you don't have the new hazard display features. The two pictures shown are from the same area. The picture on the left shows weather with the ground returns suppressed. The picture on the right shows a ground map with the weather returns suppressed. Notice the areas where the ground returns cannot be seen, indicating attenuation or radar shadowing. The weather here is strong enough that radar beam cannot penetrate any further, so the storm might be worse than it looks or may extend further than it appears. With the new control panel and hazard display features, areas of attenuation are automatically detected and displayed. Normal operation is very straightforward. You will be in the auto modes most of the time, and range selection varies with phase of flight. In most cases, detection and avoidance can all be done in auto. Think of auto mode as your protection zone. Not all weather shown as flight path will need to be avoided, but it should be monitored and may need analysis. The elevation mode will aid you in your analysis and selecting a deviation path. Here are a few simple examples to make sure the auto and elevation modes are understood before we look at some real-life operational examples. In this example, the radar is in all mode and the aircraft is flying straight and level at 20,000 feet. There is weather from 60 to 80 nautical miles ahead. So what would the pilot see on the display? The first thing to remember is the envelope is plus or minus 4,000 feet around the aircraft, or from 16,000 feet to 24,000 feet. Since this is outside of the flight path envelope, the weather is shown in a crosshatch pattern. Now let's go to elevation mode and look at an altitude slice. Remember, when the elevation mode is selected, the initial slice is at the current aircraft altitude, or 20,000 feet in this example. So what would the pilot see in this case? Nothing, because the weather is above the selected altitude slice. An easy way to think about this is in the all mode, all of the weather is displayed. It is just separated into flight path and secondary weather. In the elevation mode, only the weather at the selected altitude is displayed. Now select an altitude slice at 39,000 feet. What would the pilot see? He would see the weather above the aircraft altitude. Here is another look at the all mode, but this time the aircraft is at flight level 390. Remember that the bottom of the envelope never goes above 25,000 feet and goes to 4,000 feet above the aircraft altitude, so it extends from 25,000 feet to 43,000 feet in this case. So what would the pilot see? He would see solid green from 60 to 80 nautical miles because it is in the flight path. The red was purposely made smaller than the green to illustrate a point. The flight path weather always has priority over and covers the secondary weather. Remember, the system is giving altitude information. It is showing there is weather above 25,000 feet. So always think about altitude first, then the color. The aircraft is now at the same altitude, but the picture has changed slightly. So what would this look like on the display? From 60 to 80 nautical miles, it would look the same, but where the secondary weather isn't being covered by the primary flight path weather, it is shown but in a crosshatch pattern. So here we are showing weather in and outside of the protection zone. Now the weather is the same, but the aircraft has reached the top of descent point and is in a descent. What would the picture look like now? Since the aircraft is now descending, the flight path changes, and so will the picture. The red is now in the flight path and covers the green, which is now secondary to the flight path. It isn't necessary to memorize the altitudes the system is using, as long as there is a basic understanding about what the system is doing and showing the pilot. If there is ever a doubt about what the system is displaying, use elevation mode to look at altitude slices and build up a mental picture of the weather. Now let's look at some real-life operational examples. Recall that all radars are subject to line-of-sight limitations. The red area in this picture shows where the radar's energy is blocked beyond the horizon due to the Earth's curvature. The radar line of sight, or radar horizon, varies with altitude and is approximately 200 nautical miles at 26,000 feet and 250 nautical miles at 41,000 feet. Even though the radar energy is blocked, we can use this to our advantage. Anything that shows up beyond the radar line of sight is significant and should be monitored. But at this distance, deviation decisions are not being made. The weather at this range should be viewed on a more strategic basis. By the time the aircraft reaches these cells, they may have moved into or out of your path, increased or decreased in intensity, or completely dissipated. At long distances, all the pilot knows is they are worth monitoring. At long range, the beam is extremely large, so everything will be shown as flight path weather since there isn't adequate resolution to separate it into flight path and secondary. But again, this should not be an issue because at this distance, the weather should only be considered strategically. As the weather gets closer, it will separate into flight path and secondary weather and provide adequate resolution for analysis. New digital radar systems on the market today provide many benefits in terms of ease of use and enhanced situational awareness, but as we just described, they are still subject to the same laws of physics as their predecessors. So as we use the system, we need to keep these limitations in mind. A good way to understand the limitations is to break them down by distance or range. At long ranges, beyond approximately 220 nautical miles, the radar is only seeing weather at high altitudes due to Earth's shadowing, so any visible weather is likely to be a cell reaching very high altitudes. The beam is expanded, so cells appear larger than they really are. The expanded beam cannot see the details of the cell and will likely show only green or yellow, even if there is a red core. All weather appears as on path because the beam width is so large it cannot resolve altitudes accurately. Here we know the cell is big, but we're just monitoring the situation because they are farther away. At intermediate ranges, from 120 to 220 nautical miles, there is no shadowing effect. However, the beam is still rather large, and the weather appears very close to the horizon, making it difficult to separate low-lying weather from ground clutter. So Stratus is generally not seen at all in this area. Tall cells are easily seen and start to show better definition. The beam is still 30 to 60,000 feet tall, so they will mostly show up as yellow and green because it is an average of the energy over the entire beam width, and any red cores are likely to be much smaller than the beam at this range. All weather appears as on path because the beam still cannot resolve altitude sufficiently. Within 120 nautical miles, the beam width is narrower, and we begin to see separation between on and off-path weather, and it continues to improve as we get closer. Stratus will become visible around this range, depending on its altitude. Stratus weather may extend beyond 120 nautical miles and will show as on-path at longer range and transition to off-path when the geometry of the aircraft, weather, and beam allow good altitude resolution, usually around 80 nautical miles. Cells will begin to show red cores when present due to the increased resolution, and embedded cells can be seen separate from stratus layers. So now let's look at a couple of real-world examples using the analysis capabilities of the radar. In this example, the Honeywell 757 is level at flight level 400 over Louisiana. There are some cells with low tops and low reflectivity near the aircraft, which are non-threatening. 120 nautical miles ahead, there is some yellow reflectivity that warrants attention. The all mode display is on the left, and on the right side, a constant altitude slice is being displayed at the aircraft's flight level. In this particular scenario, the fact there is not much difference between the two displays beyond 80 miles doesn't necessarily mean all this weather is at flight level 400. It just indicates that given the resolution at this range, this is the weather that can be separated from the ground clutter. As the aircraft gets closer to the weather, the radar detects what looks like a patch of stratiform weather to the left. On the right-hand display, a constant altitude slice at the aircraft's flight level indicates there is little reflectivity aloft in that area that would indicate a potential hazard. Remember, in all mode, the maximum reflectivity from 25,000 feet to 44,000 feet is being displayed. The constant altitude slice is showing the reflectivity at 40,000 feet. The convective area ahead is showing two distinct cells. The apparent increase in reflectivity from the previous slide is caused by two factors. One, the radar is now able to distinguish the difference between weather reflectivity and ground clutter as the aircraft gets closer to the weather. And two, the radar can now resolve relatively small pockets of higher reflectivity because the beamwidth resolution is improving. At this point, the crew should expect the two cells ahead will require some type of avoidance maneuver. All other displayed weather is of no consequence. The range is now 80 nautical miles, as the cells to be avoided are at about 70 miles. A look at the altitude slice on the right-hand display indicates the cell on the right appears to be carrying a little more reflectivity aloft than the cell on the left. The all-mode display is also showing a patch of yellow reflectivity immediately to the left of the two cells. But analysis using constant altitude slices indicates the bulk of the reflectivity from this feature is not seen until about flight level 300, which reduces the threat level somewhat. Given the wind direction of right to left, the pilot should be planning a deviation to the right side of the two cells, which makes any reflectivity to the left of no interest. However, there is some weather to the right coming into view near the deviation path that will need to be monitored. 20 miles closer, the cell on the right is showing much more reflectivity, and a look at an altitude slice shows it is the only cell that is a hazard at the aircraft's flight level. The weather to the right of the two cells in the deviation path has developed into nothing of interest. When the cell is at a range where turbulence can be measured, additional evidence comes into view, the magenta color, indicating the cell on the right is the most important one to be avoided. A constant altitude slice at flight level 350 shows a clear corridor on the right-hand display for deviation around the weather. Here is another example that illustrates how the auto and elevation modes can be used to analyze and avoid convective weather. It will emphasize the use of constant altitude slices to analyze a line of convection in order to find an avoidance path. The aircraft is level at flight level 370 over Texas. On the 300 nautical mile range scale, there are two parallel lines of convective weather. The line at longer range looks rather impassable. But because the example is an actual test flight, the 757 crew will use auto and elevation modes to find a suitable path through the closer line. The 320 nautical mile display gives the big picture situation. The 160 mile display gives more detail on the closer line of storms the crew will analyze to find a deviation path. The all-mode picture by itself doesn't seem to provide much hope, but looking at an altitude slice at flight level 370, there are two small, higher reflectivity cells on each side of the aircraft's track. Looking a little higher with a constant altitude slice at flight level 400, there appears to be a potential way through. These cells are still more than 120 nautical miles away, so there remains considerable ambiguity regarding the precise ecotop of any part of the weather. But so far, the analysis shows a weak part of the line directly ahead of the aircraft. The line is now just outside 80 nautical miles, and the 757 has climbed to flight level 420. Again, the auto mode alone might be interpreted to indicate there is no path through. Looking at an altitude slice at flight level 400, the analysis shows that most of the action is to the right of track, and the potential path through is persisting. The cells in this example are now at 60 nautical miles, and looking at an altitude slice at flight level 330, there appears to be a low reflectivity path for the aircraft to go through. In this particular scenario, it probably would have been easier and safer just to go around this line to the right, but it provided a useful example demonstrating how to effectively use analysis to determine a deviation path. The RDR-4000 shows weather over a larger area compared to a conventional radar, which is a good thing. But in areas with widespread stratus weather, the amount of information can make it more difficult to process the information. This section will discuss techniques to deal with stratiform weather, including methods to identify embedded cells and a new hazard display feature to help deal with stratus weather. Stratus weather at cruise altitudes can cause a ring or halo on the display. This will appear as a fixed transition range between on-path solid and off-path hashed, indicating areas of high stratus. Depending on altitude, this can appear between 40 and 60 nautical miles on the display. The primary cause for this is that the antenna beamwidth gets larger and larger with range, as shown in the picture. A secondary cause is the 25,000-foot lower boundary of the flight path envelope in auto mode. Remember, the envelope is normally plus or minus 4,000 feet, but when you climb above 29,000 feet, which is 25,000 plus 4,000 feet, the bottom of the envelope never goes above 25,000 feet. This is because storm tops above 30,000 are likely to be frozen and far less reflective. Ice crystals typically only have 3 to 5% of the reflectivity of water droplets and are difficult for the radar to see, but can still contain strong updrafts and downdrafts causing turbulence. So for safety, we look at the more reflective lower part of the cell and show the maximum reflectivity from 25,000 feet to 4,000 feet above the aircraft. The end result is that high altitude stratus weather below the aircraft can appear as on-path weather where the expanding beam intersects the stratus layer. The range where this happens varies based on the aircraft altitude and the altitude and reflectivity characteristics of the stratus layer. If stratus is suspected, leave one side in auto mode and put the other side in elevation mode with an altitude setting approximately 4,000 feet below your current altitude. In elevation mode, there are no flight path boundaries or 25,000 foot floor like in auto mode. However, the expanding beam intersecting the stratus layer will cause a different pattern, but the transition will be at a longer range than in auto mode. And if present in manual mode, the transition will change from no weather, black, to a solid color, red, yellow, or green. But you can now easily look for embedded cells that appear separate from the stratus. Here's an example. On the left, note the transition of on-path to off-path weather at 42 nautical miles in front of us. The image on the left is auto mode, and the image on the right is a manual slice 4,000 feet below the aircraft altitude. On the right, you can see some isolated on-path solid areas that remain in manual mode around 100 nautical miles, indicating possible embedded cells. You should still use auto mode to evaluate the true reflectivity of any embedded cells. As the cell gets closer, we see more definition. In auto mode, the fixed range transition between on and off-path weather tells us we are flying over stratus weather, but a red area ahead of the aircraft indicates a possible convective cell. The manual slice, 4,000 feet below the aircraft, confirms the convective cell ahead, but it may not show the full intensity of the cell due to the frozen particles. So use the auto and manual modes together to assess the threat. As you will see in a later section, this process has been automated for Hazard Display version 2.0. The convective weather discrimination feature improves the separation of convective cells from the stratus, like the manual mode image on the right, and also shows the true reflectivity of any convective cells like the auto mode on the left. The opposite but similar situation could occur during descent and approach. As you descend and your flight path changes, the cell ahead of you will now become flight path weather, and the large area of high stratus will now be shown as secondary weather in the crosshatch pattern. Using elevation mode, you can declutter the display by selecting an altitude slice below the stratus layer, again making the cell more apparent. Another way to deal with this is by using the on-path mode. This will remove all the secondary weather from the display while preserving the flight path envelope around the aircraft. If there is ever a doubt about what auto mode is showing, the elevation mode can help you build a mental picture of the weather around the aircraft. You'll be in auto mode most of the time, and for isolated cells, the pilot can plan avoidance without ever leaving auto mode. But for cases where the pilot needs to analyze the weather and pick a deviation path, elevation mode should be used to perform the analysis. Remember, the auto modes are for the automatic detection of weather. The altitude slices are for analysis. Included in the Hazard Display version 2.0 are some improvements to help deal with Stratus. The new Hazard version 2.0 software uses a narrow vertical envelope for on-path weather, except for specific areas where convection is detected. This allows for better separation of on-path and off-path weather to a much further range, generally 100 nautical miles or further depending on the specific situation of aircraft altitude, stratus altitude, and reflectivity characteristics. These improvements to the RDR-4000 on-path weather boundaries mean we can now correctly separate stratus, off-path weather, from convective, on-path weather at much further ranges and are only limited by the effects of expanding beamwidth. Here you can see a comparison between the initial implementation and the new convective weather discrimination feature. Both images are showing auto mode. The convective weather is clearly shown in solid, and the stratus weather is correctly shown as off-path. Here is another comparison, again showing the embedded cell on the right and the areas that are now correctly categorized as off-path. Prior to the version 2.0 software, the weather may have appeared more intense because the non-convective weather was classified as flight path. So if you were operating the system prior to the upgrade, you will notice a difference in the displays, but this is to be expected. Let's look at an example with the version 2 software that will help you evaluate cells. Looking at the cell just to the left of heading at about 10 miles, the display is showing red off-path weather. The display is enunciating bar on a Boeing display, which means the gain is not in the calibrated position. So with the gain turned up and the cell at close range, there's not even green on-path relative reflectivity displayed. In other words, the reflectivity in the upper part of the cell is very low. The off-path reflectivity in the lower part of the cell is not particularly high, as can be seen in this picture, where the gain is in the calibrated position and the cell is displayed as yellow off-path. The out-the-window view shows a small convective cell that seems to be lacking in the sharply defined edges that would indicate vigorous convective growth. So everything indicates a very weak convective cell with insufficient reflectivity to display any on-path weather. In this example, the out-the-window view shows a mass of cumulus clouds that's not showing any vigorous vertical development. The radar display pictures are showing very little reflectivity, mostly off-path, with the weather at 40 miles, even with gain increased. As we get closer to the weather, it is displayed as off-path. This is consistent with weather that has reflectivity only at very low altitudes. Beyond 40 to 100 miles, it's harder for the radar to resolve low-level weather from the Earth because the weather is too close to the ground. Here the radar is able to distinguish the low-lying weather from ground and is showing some yellow reflectivity. As with the previous example, the evidence points to weak convection with very low reflectivity aloft. We'll now look at some in-service experience that will help us understand and use the system better. In the first set of Stratus examples, the left-hand display was in all mode, while the right-hand display was in elevation mode. The convective weather discrimination examples just shown combines these two views into an improved auto mode, which separates convective cells from stratus inside of 100 nautical miles, while still showing the true intensity of convective cells. So manual mode is no longer needed to evaluate stratus conditions. However, manual mode is still useful to determine cell tops and other details for weather analysis. Let's look at a couple of things that are often misunderstood about X-band airborne weather radar system. These radars are designed to reflect off water droplets of sufficient size and quantity. They do not detect water vapor, clouds, fog, volcanic ash, or extremely dry hail and snow. Rain, wet hail, and wet snow are very good reflectors of radar energy. But dry hail, for example, only returns about 3% of the energy that a raindrop returns. At times, pilots may see a cloud mass and think that it should be shown on the radar display. Large, white, puffy clouds may be a developing storm cell, but they will not show on the radar until there is a sufficient size and quantity of water droplets available. Somewhat less obvious, immediately after a storm cell is dissipated and little to no rain is falling, a dark cloud mass may still exist that hasn't broken up yet due to the wind. The pilot can try increasing the gain to see if they are just below the green threshold, but there may not be enough reflectivity available. If there's ever any doubt whether the radar is working properly, a great way to check is by using the Radar Radome confidence check. This will verify the radar is functioning and identify any issues with the radome. It's very simple to do. Cruise altitude, select map mode, and notice how far out the radar will paint ground returns. This will vary depending on altitude and the type and elevation of the terrain below. If ground returns aren't visible, or there are areas where the returns are missing, it could indicate a radar or radome problem. Also, if the radar can normally paint ground returns out to 180 nautical miles, but can now only paint returns to 80 nautical miles, or the left side of the display the radar can paint to 150 nautical miles, but on the right of the display it can only paint to 50, there could be an issue. Another item related to reflectivity that pilots observed when they first started using the new system was magenta turbulence indications in black areas. The reflectivity chart in the picture illustrates that black doesn't mean it's not raining. It's just raining at a rate below the threshold the FAA set for green, which is 20 dBz. With older radars, to detect turbulence below the green threshold, the radar would need to be about 3 nautical miles away from the turbulence in order to see it in black reflectivity. Because the RDR-4000 is much more sensitive, it can detect turbulence at the same reflectivity level from about 15 nautical miles away. The turbulence detection capability on this radar is much more sensitive and accurate, so keep it turned on and learn to trust it. Here are some items that might show up on the radar which are not weather. These pictures show a typical interference pattern usually caused by military radars. They can also be from fighter aircraft, ground-based military radars, or ground-based radars like the Port of Seattle has installed to see ships in the harbor. These can also appear as red, yellow, or green spokes on the display. They can look the same on the RDR-4000, or they can also look a little different because they are collected over multiple sweeps, motion compensated in the buffer, and separated into primary and secondary returns. The interference will remain on the display until the source is gone and the motion compensation of the buffer data moves it behind the aircraft. We'll finish this section by talking about the gain control and its use. The gain control is active in all modes, but most of the time the radar will be in the auto or calibrated gain position. The calibrated auto position is the only position where the colors represent the FAA-defined reflectivity and rainfall rates as shown in the table. The auto gain setting provides a standard reference which all radar manufacturers must follow. Immediately after turning the gain control in either direction out of the auto detent position, the man gain enunciation appears on the display, indicating that the system is no longer in the calibrated mode. Taking it out of auto allows the pilot to select -16 to +10 dB of gain for analysis. Rotating the gain control counterclockwise decreases the gain. Rotating the gain control clockwise increases gain. The gain setting has no effect on turbulence detection or display. After using gain to assess weather, it should be returned to the auto position. Using gain is really quite simple. Looking at a model of a storm cell reveals it is not as reflective at altitudes above the freezing level, but very reflective around the freezing level and below. So the gain knob is like the volume control on a TV or stereo. If the music is loud or very reflective, then one might want to turn it down. If the music is very soft or less reflective, then one might want to turn it up. So to put that in radar terms, some uses for gain are, if the gain is reduced to minimum, what is left are the strongest cells in turbulence. Gain doesn't affect turbulence detection, so any cells remaining, and especially those containing turbulence, should be avoided. Reducing gain in heavy stratus rain can also help to identify embedded cells by looking for radar shadows. Increased gain is useful for looking at frozen storm tops and can be used in analysis mode when measuring the top of cells. It is not a good practice to leave the gain control at maximum all the time, as may have been done with legacy radar systems. It could have unintentional results. With the RDR-4000, the pilot is going to see more weather, and that's a good thing. Weather at longer ranges, weather closer to the aircraft because of the 3D buffer and all the scans done at different tilt angles. Plus, the pilot is now looking at horizontal information and not just a signal diagonal slice. Because the maximum reflectivity is always shown, increasing the gain will make all of the weather appear more intense and also make more weather show up as flight path as shown in the two pictures. Here's an example of unintentional results. In the picture, the reflectivity above 25,000 feet is below 20 dBz or black, so the secondary weather, green, yellow, and red, will be shown in the crosshatch pattern on the display because it isn't covered by any flight path weather. But if the gain is increased, so the weather above 25,000 feet is now above the green threshold, it will be shown as solid green flight path weather. But remember, the flight path weather has priority over and will cover the more reflective secondary weather below it, making the weather look less intense and having the opposite effect of what was intended. Gain is mainly used to look at reflectivity information while performing analysis, and the best mode to look at raw reflectivity information is in elevation mode. In elevation mode, you will not have the unintended effects as just described with auto mode. This module describes the optional hazard display features and their operation. The Hazard version 2.0 display provides significantly more information to the flight crew on the severity and probability of weather threats. Standard reflectivity is shown by colors and is calibrated to rainfall rate according to FAA requirements, providing a probability of the weather having convective turbulence. Red weather is possibly severe, and magenta is definitely severe as its direct measurement of turbulence. Areas having attenuation are shown with magenta arcs. Lightning and hail are also directly related to the threat level, as the vertical growth and profile are analyzed to determine if the cell is dangerous. These new capabilities provide greater situational awareness to the crew and enables them to avoid areas where there is a high likelihood of a lightning strike or hail encounter. All of this is possible because of one of the unique features of the RDR-4000 system, the 3D volumetric buffer. This system automatically and continuously scans and collects weather and ground returns from the nose of the aircraft out to 320 nautical miles and from the ground to 60,000 feet. This provides a complete picture of the weather and automatically detects and accounts for varying worldwide weather conditions. Continuously collecting and displaying this composite information in real time prevents overscanning hazardous weather. The scanned information is stored in the 3D volumetric buffer, or memory. This provides a database of live storm cell information that can be analyzed to provide information on measured and predicted hazards to the crew. This allows the RDR-4000 system to provide enhanced hazard display features. As mentioned, some are based on measured data and some are predictions. The extended range turbulence, attenuation detection, weather turbulence ahead alerting, and convective weather discrimination features are all based on actual measurements. Hail and lightning cannot be directly detected by airborne weather radar. However, the data in the 3D volumetric buffer can be analyzed to determine whether conditions are conducive for these hazards to develop. When this is the case, icons are displayed to convey this information to the crew. The hazard display features are supported by a new control panel distinguished by turbulence and hazard display buttons. Enhanced turbulence detection is already included in the baseline RDR-4000 system. It provides greater sensitivity, fewer false alerts, and improved correlation to the predicted G-forces on the aircraft compared to traditional turbulence detection. In the baseline system, the magenta turbulence indications are provided out to 40 nautical miles for any range selection and plus or minus 5,000 feet around the aircraft altitude. Because of the increased sensitivity of the RDR-4000 system, we are now able to provide extended range turbulence out to 60 nautical miles for all range selections. It is shown on the display in the same manner, but in the auto modes it will match the flight path envelope. With the hazard detection features, it is also available in elevation mode and is shown for the selected altitude slice. Turbulence is selectable on and off, and by default is on at power up. We have also added an attenuation detection and display feature called REACT, or Rain Echo Attenuation Compensation Technique. We have used a version of REACT in our general aviation and business jet radar since 1980, but because of limitations, we did not introduce it in our air transport radar systems. The previous versions of REACT were very dependent on correct tilt setting and did not perform well when the gain control was not in the auto or calibrated position. The RDR-4000 implementation overcomes these limitations. REACT indicates areas where the radar signal has been so severely attenuated by intervening rain that the radar can no longer accurately report the strength of weather that is farther away. REACT not only shows the azimuth location of the attenuation, but where it occurs in range, represented by purple arcs. In the picture on the left, a line of very strong cells has attenuated the signal to the point that the radar beam cannot penetrate any further, so the storm might be worse than it looks or may extend further than it appears. In the picture on the right, there are areas just to the left of center that, although attenuated at longer range, represents a true picture of the weather up to the purple arcs. Now that we have all this data in the 3D weather buffer, we are able to do some more interesting things with it. By looking at vertical columns of the weather throughout the buffer, we are able to find areas of convection. Then, applying some additional information, such as altitude and intensity of reflectivity, we are able to predict areas that will produce hail and/or lightning. These areas are represented on the display as icons, indicating the range and azimuth as shown. Hail and lightning icons indicate that conditions are conducive to the development of hail or lightning. They do not guarantee that hail or lightning will be present, nor does the absence of an icon guarantee that the condition will not be present. The icons indicate general areas or storm cells that are likely to produce the condition. They do not indicate precise boundaries or keep-out areas, and you can't be safe just by avoiding the icon. The icon indicates that this cell is likely to be worse than other cells. Keep in mind that these are predictions. However, testing has shown very good correlation to ground-based sensors. In tests, we achieve better than 93% correlation. We say better than 93% because in some cases we produced icons in areas where the ground-based sensors did not, but 5 to 10 minutes later there were actual lightning strikes. So it proved to be a good leading indicator of lightning activity. The logic behind the hail and lightning icons is based on the identification of three-dimensional hazardous convective areas, the current aircraft altitude and vertical flight path. Once a cell is determined to contain a convective hazard, either lightning or hail, a protection zone is established within the vertical column for that hazard from 4,000 feet above the highest reflectivity all the way to the ground. The reason for this is that hail falling from above is a hazard down to the ground, and lightning tends to discharge from the source to earth, although in some cases can go cloud to cloud. So the area below the cell is considered hazardous in this case as well. The recommended deviation around these cells is at least 20 nautical miles because both of these hail and lightning hazards may not discharge directly below the cell. In auto mode, the radar determines where the vertical flight path, the current flight path, altitude plus any climb or descent profile, passes through a convective hazard zone. In elevation mode, the selected reference altitude is used to determine the regions where it passes through these hazardous protection zones. Given the logic between auto and elevation mode and the fact that the hazardous zones extend all the way to the ground, you will see the same icons when using manual mode and selecting a reference altitude below the current vertical flight path. Note, there are some other reasons these may be different, such as range settings or degraded threats from hail to lightning, etc., but this is generally true. The manual mode icons may be different when selecting a reference altitude above the current flight path, where the selected altitude is above more than 4,000 feet above the highest reflectivity. This is the reason you can see an icon in elevation mode with no associated reflectivity. Also note that a hail icon may be downgraded to a lightning icon when looking at manual altitudes above the auto mode flight path. Be aware that some exceptions may exist to the cases described due to the logic behind the minimum hazard size, icons consolidation, range setting, etc., which can cause the icons in manual mode to be removed even if some reflectivity remains. Hazard version 2.0 also contains a new feature called Convective Weather Discrimination that we discussed in the section on dealing with stratus weather. Again, we can analyze the data in the buffer to help aid in threat analysis. This feature helps separate high-level stratus, which is not threatening, from convective weather, which is dangerous. It puts the stratus into the off-path weather display, hashed, and keeps the convective cells in on-path, solid. The results are fewer unnecessary flight path changes around non-convective weather and early detection of embedded convective cells, providing increased safety and efficiency. The left side shows a sequence of real flight data using the current software with convective cells embedded in a layer of stratus. The system, like all weather radars, has a difficult time separating the convective cell from the stratus layer until at very close range. The right side shows the same sequence of flight data where the convective weather display function separates the stratus and displays it as off-path, while identifying the convective cell and showing it as on-path. This provides better situational awareness of real hazards at longer ranges and also properly shows the stratus so the pilot is not tempted to unnecessarily divert around the entire area of weather. The last new feature of the Hazard version 2.0 features is weather ahead alerting, which is unique for Airbus and is only available on the Honeywell radar, so it's unique for us too. This feature provides an automatic notification to the flight crew of significant on-path weather along the current flight path. It covers two important conditions. One, the pilot is not monitoring the displays and doesn't notice severe weather. And two, pilots forget they have turned the gain knob out of the calibrated position or have selected manual mode, which is not showing the hazard. The alert corridor is 4 nautical miles wide and out to 3 minutes ahead of the aircraft and covers plus or minus 4,000 feet around the aircraft's altitude. There are 3 hazard levers. 1, no alert. 2, WEX, meaning yellow or red returned. And 3, turbulence. An advisory text message, weather ahead, is displayed when the aircraft altitude is more than 1,500 feet AGL and weather or turbulence hazards are detected within the corridor. An oral alert, weather ahead, occurs when the weather or turbulence hazard level changes to a higher level and all the following conditions are met. Weather is not selected for display on either ND, and the aircraft altitude is more than 2,500 feet AGL. A hazard level change is defined as a transition from no alert to yellow or red returns in the corridor, or a transition from yellow or red returns to turbulence in the corridor. We'll finish with a quick summary. This is mainly to point out the differences for existing operators who are adding the new hazard display features. With the hazard display features, turbulence detection has been extended to 60 nautical miles and is also available in elevation mode. In the auto modes, it is shown for the flight path envelope, and for elevation mode, it is shown for the selected altitude slice. Hail and lightning icons are shown for the first 160 nautical miles in all WEX, path WEX, and elevation modes. Attenuation detection is shown in the all WEX, path WEX, and elevation modes. Convective weather discrimination is used in the auto modes. Weather alerting is on by default all the time and is shown in all modes including ground map and will pop up even if weather is not selected for display. Turb and hazard are selected by default at power up. Listed here are some additional resources for the RDR-4000. Thank you. We hope that this has provided a solid basis for understanding the Honeywell RDR-4000 weather radar system and its capabilities.